All right, taking a look today specifically at our parabolas, which is the graphs of our quadratics. That shape is a parabola shape, so it's a very special shape. It's used quite a bit in architecture, computer programming. It just shows up a lot within nature as well. There's a lot of different things out there that have that parabola shape. So it's very important. We use it a lot. So we're going to go over some of the characteristics of this, which you should have done back in Algebra 1. So hopefully quite a bit of it is review. These are all our main characteristics that we are going to talk about. So we got our x-intercepts, which are your solutions, your roots, and your zeros. Your y-intercept, your axis of symmetry, your vertex, leading coefficient, domain range, increasing, decreasing. So a lot of this is review of what we have been doing in the last couple of units. We're just kind of narrowing in a little bit more on that parabola shape. So let's take a look at the inside. So here I have the graph of a parabola on there already for us, so we can take a look at it, analyze it, discuss all the different parts. So again, our x-intercept, which are your solutions, roots, zeros, so many different names that we give to those x-intercepts. So we call them solutions because when you are solving algebraically a quadratic equation, you are solving for the roots. So those are the solutions also to those algebraic equations. That's what we're actually solving for, is where it ends up on that x-axis. So here we have two x-intercepts. X-intercept, x-intercept. So I'm going to call them root 1 and root 2. It does not matter which one I call as root 1 or which one I call as root 2. They're just both roots. So we write our x-intercepts as x equals. The majority of the time, that's how we write them, because when you solve them algebraically, this is what you get as your answers. And we're going to talk about our algebraic solving in a couple of days. So when we're solving them algebraically, we're getting our solutions. This is how we write them. You will see some people write them as a set of points, but the majority of the time, this format is the one that we are looking for. X equals 1, x equals 5. So that's how you'll see me write it the majority of the time. So moving on to our y-intercept. We're all pretty good with y-intercept. That's where we hit our y-axis. It's your y-axis. The other important thing about your y-intercept is in word problems, this is where your starting point is going to be most of the time. So like if we're dealing with a word problem and it's like a projectile motion problem, and let's say you're shooting a rocket off of a cliff, well, you're going to be starting up here on the y-intercept. That's where you're going to be, on the top of the cliff. So that's why I say for our word problems, a lot of times that is our starting point. So that's why that's an important number for us to be able to identify on our parabola there. So next up, we have our axis of symmetry. So that is our imaginary line down the middle. So when we draw that in, we always draw it in as a dotted line because it is imaginary. Axis of symmetry. And what that does is it breaks our parabola in half. If you remember the definition of symmetry, it means that it's identical on both sides. So that axis of symmetry, if we were to fold our piece of paper on this line, our parabola is identical on either side. It's mirror images of each other. So our axis of symmetry for this one would be x equals 3 because it hits the 3 on our x-axis. If you need to calculate it out, it's that formula x equals negative b over 2a. So you would use your equation, which I have right down here. B is that value in front of x, A is the value in front of your x squared, and then you plug it into your equation. So here my B is a -6, so I would plug in a -6. My A is a 1, so I would do 2 times 1. And then I can plus. So 6 over 2 gives me 3. So we get the same answer algebraically. We would use that equation there. So that's our axis of symmetry. Axis of symmetry is used, again, in a lot of word problems to help you find your maximum value there or your minimum value, depending on which kind of an equation you have. So our vertex, also known as our turning point, for this one we have a minimum, and our vertex here would be at the point 3, 1, 2, 3, -4. We don't have a maximum on this graph. If we were to have a maximum, it would be for an upside down parabola. That one would have a maximum value to it. We can find our vertex algebraically by taking your axis of symmetry, that is the x portion, and you would plug that into your equation, and that would give you your y value to it. So if you notice here, again, my vertex and my axis of symmetry, those have the same x values because they go through the same x portion. See, here's your axis of symmetry. There's my minimum. They share that x value, and they always share that x value. It always will happen that way. So if you need to find your vertex algebraically, you start with your axis of symmetry formula, plug that number into your equation, and then that gives you your y value. So the rest of your turning point is there. Okay, our next portion, leading coefficient. So again, if we are in standard form, which is your y equals ax squared plus bx plus c, your leading coefficient, so that value right there in front of your x squared, if it is positive, that just means your parabola is going to open up. If that a value is negative, that means your parabola is going to open down. Okay, so positive a means that it's going up. Your range is going to be a greater than. Your turning point is going to be a minimum, whereas if it's negative, that means it's pointing down. Your range would be a less than or equal to, and you would have a maximum value. So that leading coefficient can help you tell you that information without even really looking at the graph. Right. So before we get into domain and range, I just thought of something I wanted to point out to you also with the axis of symmetry. So the axis of symmetry, again, that goes through our middle. So what I wanted to point out is it's in the middle of your roots as well. So here's my axis of symmetry. It's 2 units from that root, and it's 2 units from this root. So no matter where those roots are, your axis of symmetry is always going to go through the middle of them. I point that out because sometimes we have questions where they give you one root and you know where your axis of symmetry is, so you just have to be able to find your other root. And again, it's going to be the same distance away on the other side of your axis of symmetry because it goes through the middle. So that applies even to those roots. Okay. Domain and range. Domains for our quadratics. This is not one of our restricted cases, so it's XER, or negative infinity to positive infinity, depending on which notation it is that you like to use. Our range for this one, -4 is my minimum, and then it's going up, so it's everything higher than that. So y is greater than or equal to -4. Interval notation would be bracket -4 to infinity. Now, if this had a negative a value and it was pointing down, my range would be a less than. But because it's pointing up, my range is a greater than. And then our last one here, increasing, decreasing. So that axis of symmetry, that's also your division between when you're increasing, decreasing. This parabola starts decreasing first, so it is decreasing until it reaches your turning point. And then it switches, and now it's an increasing graph. So again, your axis of symmetry at 3 is where it changes. So it's increasing when x is greater than 3, or 3 to infinity. And it's decreasing when x is less than 3. So negative infinity to 3. Okay. So then down over here, we're going to talk a little bit more on the next piece of paper about these, but we have 3 different ways that we can write the same quadratic equation. We have our standard form, which is definitely our most common form. You've used this one a lot in Algebra 1, because when solving quadratics, generally you would put that into standard form and then solve it from there. So again, we have our ax squared plus bx plus c. That is our standard form. This being an x squared, that always goes first. Your largest exponents always go first. And then this is an x to the first, and then your 5. That is the order our standard form goes in. And because our largest exponent here is a 2, this is what we call a degree of 2. This is a second degree equation. Okay. Our linears are a first degree equation. This is a second degree equation. Linears are first degree because they're x to the first. Another form for our quadratics is what we call factored form. We'll be practicing factored form a lot more. So it's just another way of being able to, again, write that equation. But the nice thing about factored form is it helps you see your roots much quicker. Because if you remember, we set these equal to 0. And then we finish solving. So I on this side, I'm going to zoom in a little bit more so you can see what I'm writing here. There we go. So on this side, I would add my 1 over. So I end up with x as a positive 1. Here I would add my 5 over, and I end up with x as a positive 5. So your factored form is just the opposite sign value of your roots. So the factored form is nice because then we can find those roots or solutions very quickly because we just change the signs, and that's what your roots are going to end up being. Now, this is still a degree of 2 because you would have to multiply x times x, which would make it x squared. So it is still a degree of 2. It's just a different way of being able to write that degree of 2. And these are the same quadratics. Again, just different ways of writing them. And then our third way to be able to write a quadratic is our vertex form. So our vertex form is nice for several reasons. One reason is you can find your vertex right away from the equation. So here our vertex would be the 0.3, -4. You always change the sign value there, because if you remember from our transformation rules, minusing that means that it's actually you're plugging in a positive, because that normally is x minus h squared. So really that is a positive 3 that we're using. This stays exactly the way it is. So our vertex is the 0.3, -4. That's helpful, especially when you're dealing with word problems that need that vertex, because you're looking for your maximum value or you're looking for your minimum value. Bam, it's right there in the equation. You don't really have much work to do. The other thing is you can easily see your transformations. So if you don't have your calculator, you're trying to graph it, your transformations are nice because you can see where your vertex is, and then you can move it 3 to the right and then down 4 like we were just talking about in our last unit. So these 3 forms are the different ways we can write our quadratics. And these 3 equations are all for the same quadratic. Now if we're using our transform, yeah, so if we're using our transformations, our quadratics always follow the same pattern with the points unless there's a dilation. It's up 1 over 1, up 3 over 1, up 5 over 1, and then if you guessed it, it would be up 7 over 1, up 9 over 1. So it always follows that pattern, and because our axis of symmetry means that it's a mirror image, you just repeat it on the other side. So it's still up 1 over 1, up 3 over 1, up 5 over 1, up 6 over 1. You just go to the left instead of the right for that. And then if it's a dilation of 2, these would all get multiplied by 2. So it'd be up 2 over 1, up 6 over 1, up 10 over 1. So that's how those dilations affect that pattern. All right. Let's take a little bit more look at this one here. Again, these are different ways to represent quadratic functions. We have lots of different options. Each option tells us a different piece of information about that quadratic function. So sometimes one form is more helpful than another form. All right, so let's say I have the quadratic of x equals x squared minus 8x plus 15. So this is helpful if I was then going to try to factor and solve it, which again we'll be practicing later. But that's really all standard form really helps us do. It doesn't really help us do too much more than that. We can't really get too much information out of it. We could plug it into our calculator to get our table of values so that we can graph it. So if I factor my trinomial here though, multiplies to 15, adds to give me a negative 8 since it's in 1x squared would be x minus 5 times x minus 3. So my factored form is nice because I can see that I'm going to have roots at 5 and 3, because again, my roots are just going to be the opposite sign values of that. So 3 and 5, those would be my roots over there. I'll zoom in on the graph a little bit more in a second. So I can then use that to help me finish my parabola without using a calculator. So I can see because these are only 1 apart, that means my axis of symmetry is going to end up being right there where x is a 4. So my pattern for the quadratics is that's going to be a 1 because it's going to be, or down 1 I mean, because it's going to be up 1 over 1 to get to that point, up 1 over 1 to get to that point. So now I go up 3 over 1. And then I reflect that over on the other side, and then up 5 over 1. Oops. Reflect that on the other side. There we go. So there's my graph. So I can always use that factored form to give me my 2 roots, figure out where my roots are within my parabola pattern, and then I can graph my parabola. So here I have a vertex at 4, negative 1. So my vertex form, which is a times x minus h squared plus k. We will learn how to do this algebraically, but for now, you can get your vertex off of the graph. Your a value would be the same as your a value from standard form, which is just a 1, so this is going to be x minus 4 squared minus 1. That would be our vertex form. So other things we could do is to help us get our vertex form. We could use our negative b over 2a formula. So our axis of symmetry would have been at 4. Then we could plug that in. We'll do that on the next one. All right, let's try another one. So let's say I have this time g of x equals negative 2x squared minus 4x plus 6. All right. So let's do our vertex form. So for vertex form, I'm going to find my vertex algebraically. So I'm going to start with my axis of symmetry formula, negative b over 2a. My b here is a negative 4. My a here is a negative 2. B is in front of x. A is in front of x squared. So that's going to be negative negative 4 over 2 times negative 2. And just 4 over negative 4, so x equals negative 1. So my axis of symmetry is going to be x equals negative 1. So I'm actually going to go over to my graph and draw that. Bam, axis of symmetry. So now, the one part we haven't seen yet, so I'm going to plug my negative 1 into my equation. So negative 2 times negative 1 squared minus 4 times negative 1 plus 6. So that's going to give me a negative 2 plus 4 plus 6. That's going to give me 8. So that means my vertex is going to be the point negative 1, 8. So I plot that point right there. So my vertex form, again, it's going to have the same a value as my standard form. My a value is negative 2, so my a value here for my vertex form is also negative 2. And it's going to become x plus 1 squared because it would be minus negative 1 plus 8. There's our vertex form. Same function, just writing it in a different way. All right. Now I'm going to put it in factored form. So I'm going to factor this. I see a GCF of negative 2, so I'm going to take care of that first. So now factoring this trinomial multiplies to 3, adds to 2 would be 3 and 1. My 3 would be positive to make that 2 positive. And there is my factored form. So I can tell from my factored form I'm going to have roots at negative 3 and positive 1. All right. So now then finish off my quadratic. This has a dilation of 2. Looking at our transformation rules, this would be a dilation of 2. That negative made it reflect. So that means I'm going to go down to the right. Oh, you can't see that. From my vertex down 2 to the right 1. It's down because it's negative. So that's going to be a downward sloping parabola. And then this is down 6 to the right 1. And down 10. Oops, I lost count. 1, 2, 3, 4, 6, 7, 8, 9, 10, over 1. There we go. Again, you can always get points from your calculator to make your graphs as well. So if you can't remember the pattern, that is completely fine. Let that calculator help you. It is there for that. So again, 1, 3, 5, 7, 9 is the normal pattern. Dilation of 2 makes the pattern a 2, 6, 10, 14. It just doubles each of those. All right, let's do one more. We're going to go backwards. Well, not backwards. We're going to start with a factored form this time. All right. Here we go. So I have roots at 6 and 8. So if you haven't already, 6 and 8, 2 dots right there on the x-axis. So I'm actually going to go into standard form first because factored form to vertex form, that doesn't really work out very well. I can't find my axis of symmetry from my equation. You could probably figure it out from your graph easily enough, but we can't figure it out from the factor form equation. So I'm just going to multiply all this out in order to get my standard form. So I'm going to multiply my two binomials out first. So x times x is x squared, x times negative 8 is negative 8x, negative 6x plus 48. Distribute twice. Distribute the x to both, distribute the 6 to both. So 18 or negative 8x, negative 16 or negative 6x gives me 14x. And then I'm going to negate everything. And there's my standard form. So negative x squared plus 14x minus 48. So again, standard form doesn't really do a whole heck of a lot for us. We could type it in the calculator, but also you could have typed it in factored form to get your table of values as well. Both of them are fine. All right, so let's practice calculating our axis of symmetry. So negative b over 2a, my b was a 14, so I made a negative 14. Negative 14 divided by negative 2 gives me a 7. So axis of symmetry is going to be at 7. I'm going to go draw that in on my graph. Bam, there we go. So my graph has my two roots that I got from my factored form. My axis of symmetry I just calculated. So now I'm going to figure out the rest of my vertex. So plug in 7. I got negative 49 plus 98. So that's 90 or 49 minus 48 gives me 1. So 7, 1 is my vertex. So I'll plot that one. So negative x minus 7 squared plus 1 is our vertex form. Again, we'll practice in a couple of days how to find that algebraically. So I'm going over here, I'm going to complete my pattern. So I got the 1, 1. So I'm going to do the 1, 2, 3, 1. And again, this needs to be going down with the pattern because it was a negative. 1, 2, 4, 5, 1. I won't be able to do 7, 1. There's our graph. So 4 ways to be able to show the same quadratics. Each way gives us a different piece of information. Each way has its own usefulness. All right, so we're going to be practicing that. We're going to be going back and forth between the different ways because, again, the different formats have different pieces of information about the quadratic for us. So, I mean, ultimate goal is we want to try to do it without a calculator, but it is always, there is a backup option if we need it.